Is this appearing fine?
Yeah, beautiful.
Okay. Good. Hi, everybody. I'm Vaishak, and thanks to the organizers for this invitation. This is a bit different from what Matthew was talking about, but still very related. On the one hand, it zooms out a bit, looking at more broader schemes for combining deductive reasoning and machine learning. And on the other hand, there are some key ideas here that relate to some of the things that Matthew was talking about and the other sessions in the morning. So roughly what I'll do today is very quickly kind of tell you about, these two camps that we know and kind of aware of in AI and other areas as well. There's deduction and induction. I'll cover some fundamental insights that bridge logic and learning. Again, this is only about teasers to some of the key ideas. There's a longer 45-minute tutorial that's on YouTube, and there's also a book chapter that discusses in detail and surveys the ideas that I talk about here. So very quickly, for those of you who are working in AI, you're well aware of this, but if you're not, one of the fundamental issues, at least in artificial intelligence, is that for the first 40 years or so, there was a lot of logic, and for the next, it seems, 40 years, there's machine learning. And clearly, they seem to be at two ends of the spectrum. But as I kind of discuss here, this is really not the case. In some sense, deduction is concerned with representation, concerned with reasoning, coming up with proof systems, coming up with verification techniques, and so on. So this is typically the domain of formal logic, as we all know. Whereas machine learning is, of course, about trying to generalize from examples, from partial descriptions. So typically, we talk about random variables, probability distributions. Deep learning is just one instance of the broader learning camp. But to a broad degree, there are numerous crossover areas, everything from statistical relational learning to neuro-symbolic systems to high-level control to verification, like the kind of stuff that Matthew was talking about, which have illustrated that this dichotomy is kind of not very constructive. And we also recognize that deep learning, despite being quite significant in trying to generalize from examples, they do have tons of problems, from robustness to issues of transferability to issues of causal understanding, explainability, data efficiency, and so on. And it does seem to be the case that the trend is that people are trying to take ideas from programming languages and logic to try and empower what is happening within deep learning. There is also this kind of human cognition perspective, which is kind of interesting, which is often compared to this Daniel Kahneman's so-called system 1 versus system 2, where you might have low-level data-intensive computations that you need to interface with high-level thinking, right? So you can think of this as kind of providing a specification language that is readable to you and me, but at the lower level, it might pick up on observations that are fairly hard to grasp, and where machine learning might be more useful, and you need some way to bridge these two planes of function, right? So what I'm trying to do here in this very quick survey is to not really resolve this debate, but really say that there are ways we can think about the connection for this, and broadly they could be thought of in the following ways, right? We can think of logic and machine learning trying to do the same thing, but with their independent tools, and I'll explain that in a minute. We can think about using machine learning for logic, so this might include, for instance, the learning of logical artifacts, formulas, programs, properties, whatever you want. We can also think about logic for machine learning. So for instance, if you think about verification of deep learning, this is one instance where we're using logic to help out certain machine learning things. We could also use logic to kind of delineate the boundary between tractable and intractable problems. There's a very rich space for which logic can contribute to machine learning as a kind of meta theory, right? Providing a theoretical apparatus that allows us to really dig deeper into what machine learning is doing and try to identify islands of tractability and so on and so forth. So the whole space of different ways logic and machine learning can interplay. One quick point I will make is that there is this very common misconception that, let's use logic for discrete properties and we'll use probability theory and machine learning for continuous properties, but this is a misconception, okay? So it's true that logical formulas are discrete structures, but they can express continuous or countably infinite properties. And that's one of the things I also talk about in this survey, but I'll omit it in this talk. Feel free to look it up if you're interested, to look at how logic logic can also help in the continuous and the uncountably infinite aspect of machine learning. So there are many ways it can contribute. Let's quickly look at how logic and machine learning can compete against each other. Okay, so the idea here is that can we use logic-based techniques to basically look at classical machine learning problems and see if something can be improved? And to see how this all fits in, many of you might have seen these diagrams of this sort. So this is a Bayesian network. What it's trying to capture is that there is a random variable A, and A is influencing B in some sense. Okay, so you can think about, if it rains outside, you walk out with an umbrella, and there's a certain probability that you will take this umbrella depending on the likelihood of rain. Okay, so the way you would specify this is using what is called as a conditional probability table. So you define the probability of A. Because A has no parents, you give it one probability for each outcome, whether it rains or it doesn't rain. And then for B, you define this kind of conditional specification where you say if it's A is true and B is true, the probability of this event is 0.6, so on and so forth for all possible outcomes. Now, if you look at this, right, for those of you who are familiar with logic, you will immediately see that this is really like specifying all possible propositional interpretations for the two propositions A and B. Okay, and this is a fundamental idea that shows that underlying probabilistic computations is really a logical kind of computation as well. So it's like thinking about all possible propositional interpretations for these two propositions and assigning weights to these things. Okay, but it can go a step further. So, for instance, this is a framework known as Markov logic networks. What it does is on the left-hand side, you see logical clauses. So you see things like if X is a smoker and X and Y are friends, then Y is a smoker too. Now, this is not an absolute fact. This is a question of influence. So you attach a certain probability to this. It turns out that there's a very neat way to see these kind of weighted logical specifications as a kind of Markov network. Okay, so a Markov network is an undirected network, which is typically very popular in physics in the 60s and 70s, but it's also widely used in machine learning right now to understand images and that kind of thing. And you kind of see that you can specify something logically, and that has a very close correspondence to a probabilistic specification. Now, the interesting thing is if you don't specify any weight to a logical sentence, like the case we have at the bottom, where it's basically saying that asthma, spreads in the family or exists in the family in the gene pool, you kind of see that this becomes a so-called hard constraint. Okay, so which means that in every possible distribution, this must be true. So you can use logic to construct fairly intricate distributions. This is another example using a logic programming language called as Problog, where what you have is you have two coin tosses, okay? And in the first case, the probability of it falling heads is 0.5. In the second case, the probability of falling heads is 0.6. So the second one is a biased coin. And what you're looking at is a composite event. You toss both the coins. What is the probability that you get two heads, right? So this is a way of specifying interesting and fairly difficult probability distributions. But again, in the end, you're using logic to kind of specify these distributions. Now, what does all of this have to do with SAT? It turns out that you can take these whole sequence of different kinds of languages and frameworks, and when you look at the fundamental computational property underlying them, it turns out that they can all be phrased as SAT problems. Okay, so basically in SAT, what you try to do is you find a satisfying assignment to a propositional formula. It turns out that if you try to find all possible assignments to a propositional formula, it basically reduces to a probability computation, which is exactly what any of these languages need. Okay, so there's a way to really look at the entire spectrum of probabilistic languages, from factor graphs to Bayesian networks to databases to probabilistic logics and Markov logic networks, and reduce them to the SAT problem. And there's a variety of techniques that we can use, including SAT solvers, for solving this. And we end up getting this fairly comprehensive and generic way to solve probabilistic computations. Okay, so just to remind everybody very quickly, typically in SAT you have a CNF, what is called as a conjunctive normal formula, which for instance the one on the top says that either X or Y is true and Y or not Z is true, and you can find one possible assignment, which is what a typical SAT solver would do. And you can see that if you substitute X with 0, Y with 1, and Z with 0, this formula ends up becoming true. Okay, so what you're now interested in is the counting version of this problem, where you're looking at all possible assignments to that formula, and that's called a sharp set. And as I said, once you compute the sharp set, there is a very nice reduction to a probabilistic computation, and so you can use SAT solvers as a generic engine to compute the probabilities in Bayesian networks and Markov networks and so on. Okay, it turns out that you can also have a continuous version of this, and again, this is something I won't go into details about. And instead of using a SAT solver, you would use an SMT solver. So for those of you who are familiar with using SAT solvers and so on, this might be a nice connection that you may not be familiar with, that there is a way to take all of the expertise you have with SAT solving and convert it to the very essence of machine learning computations, which is probability estimation. Okay. So let's consider the second category, where we're looking about how machine learning could be used for logic. And it's clear why we need this, right? So logic is great for writing things down, but at some point you need to be able to induce structure from data, right? You cannot be expected to write around every axiom that is needed for your domain. So the property of trying to learn from data turns out to be extremely important for the logic enterprise. And there's a very long history. Certainly in computer science, everything from program induction to plan synthesis are all examples of trying to use machine learning for logic. Okay, so there's a lot of work in the propositional and finite automata settings. Very broadly, I'm just conscious of the time. I guess I have another 10 minutes, right, Katya?
Yeah, no, you're okay. Go ahead. We're late, so I actually lost count of time. It's an interesting topic. Go ahead.
Okay. So very broadly, if you look at the entire spectrum of how people have been using machine learning for logic, it broadly fits into these two categories, okay? One category is a so-called entailment-based scoring, where what you're doing is that you have some kind of logical language L, you have background knowledge B, and what you want to do is, given some data D, you want to find a hypothesis, right, H, such that when you take B and H together, they entail the instances in D, right? So this is classical for if you're familiar with inductive logic programming, this fits in that regime, okay? Now there's a complementary way, the kind of Bayesian way, if you want to think about it, of looking at the same problem. In fact, this goes back to philosophers like Rudolf Carnap, and what this one is saying is that let me pick a hypothesis, right, H, such that the probability that the data is captured by this hypothesis is extremely high, okay? But on the other hand, I don't want a hypothesis that simply replicates the data. So I will penalize the complexity of this hypothesis, okay? So this is the size of H as it's written down in this equation on the second line. So basically you're trying to balance a good fit for the data, but you don't want to overfit, right? Which makes sense. This is what most machine learning people do in non-logical sense anyway. And between these two schemes, right, between entailment-based scoring and likelihood-based scoring, there's a whole range of options we can look into now. And certainly, if you're following the recent trend in ICML and Europe and so on, people are trying to mix and match these things, right? People are trying to use Bayesian scoring for entailment approaches. People are trying to use neural techniques to do likelihood-based scoring. There's also a lot of theoretical work where they try to guess a hypothesis without, in the sense of being correct with respect to what examples you have not seen, right? So typically what happens with some of these approaches is that they say, given this data, I will guess a hypothesis that's the best fit for the data. But if you give me new data, I might have to throw this hypothesis out. So there are approaches now that try to look at the data that you've seen, try to construct a hypothesis that is robust to examples you have not seen, okay? These remain mostly theoretical approaches, but there are some practical advances as well with fairly strong results. So let me give you one example of this, okay, just to pick your interest. I assume most of you haven't seen things like what's on the right-hand side. So what this is a so-called tractable structure, okay? So it looks like like a circuit, right? If you look at the pluses and the crosses, you can think of this as sums and products, or you can think of them as ands and ors. And what it does is it looks through the data, it identifies the distribution for a certain atomic entity, okay? And then it starts to cluster these entities using either ands and ors. So basically it constructs a logical formula from the data, okay? Interestingly, this is now being shown to be fairly competitive to standard deep learning networks. So there's a variety of papers from everyone from Zubin Garmani to Christian Kirsting who have looked at these approaches, and they're trying to say, well, deep learning is great, but what it captures is purely the conditional distribution, right? You're optimizing for the label, whereas with these models, you can build a generative distribution. So if you look at the third item point here, typical networks, deep networks would try to obtain the probability of y given x being the data and y being your output, whereas now you have a generative approach for the same problem, which is much richer, okay? So these are very interesting structures coming from logic, which are proving to be incredibly useful in the machine learning landscape. To the very final section in terms of the bridge between the two things, let's look at how logic can be used for machine learning. And we've already seen instances of this. A classical thing that people are looking into, like what Matthew was talking about, is trying to verify machine learning models using logical specifications on the one hand. But there are a whole bunch of other things. There are these loss calibration approaches, as well as relational embeddings. What they try to do is they try to train a deep network by forcing the loss function to respect some kind of constraint. I think the monotonicity property is another thing which Matthew talked about. You could see monotonicity also as a kind of loss calibration in certain approaches. There are also logical alternatives to standard machine learning, like the thing I mentioned in the last slide, which are circuits. I'll preview something else very quickly in the interest of time. An area of research called as probabilistic programming. Maybe some of you have heard of it. So what probabilistic programming tries to do is that it tries to bring probabilistic primitives to programming languages. Okay, the reason you would want to do this is that rather than trying to simply call machine learning modules using APIs, you might want to have primitives in your programming language that can capture the randomness in a machine learning model. Okay. Let's look at some examples. One I already talked about in a previous slide, where you have two coin tosses, right? And you're looking at the composite event of getting two heads. One is an unbiased coin and the other is a biased coin, and you want to look at the composite event, okay? Here's one where I'm trying to model the spread of disease like COVID, but obviously not as complex. This is a very simple example. What I'm trying to say here is that, there's a certain probability that two people come in contact. There's a certain probability that there's an influence. So influenza spreads, right? If two people are in contact and one person has influenza, the other person might also catch influenza. And we query the distribution of how this is spread, right? So if you think about this problem, it's fairly complex and it might take you a while to work out a model, but with a few lines of code, you can actually specify the spread of the disease fairly compactly. Now, the interesting thing, of course, is that if you go to a different data set, a different population, where the probabilities might be different, the model remains the same, right? The rules remain the same. The only thing that would change are the probabilities. So you get a kind of a skeleton to really model different scenarios in different population sizes in a very clear and clean way. Here's another piece of work that we did a few years ago, where we looked at probability problems, okay, written in natural language. So things like, you roll a fair six-sided die twice. What is the probability that the first one gets a 5 and the second one shows a 6? Okay. Now this is obviously a probabilistic model, and the way you would solve this, typically in GSEs and in school, is that you would try and write down the formula for this and try to work out whether it's a repeat or a non-repeat, et cetera. And we were able to show that there's a way to convert these natural language questions to a probabilistic program, right? And basically it spells out in code exactly what is specified in the natural language. And of course, now you have a kind of declarative way of solving these problems that shows you how exactly by combining these two events, you get the final event, the question you're really interested in, okay? So this is a way that logic is really proving to be fairly powerful to kind of tame machine learning and make it a bit more modular. So just to wrap things up, as I mentioned, the connections between logic and learning are very deep. The range goes from coming up with alternative computational schemes, like we saw with SAT solvers. We can look at expressiveness and representation. We can use logic to kind of push what machine learning models typically don't think about, like relations, think about logical properties, so on and so forth. And finally, we can think about contextualizing. This is to verify machine learning models, add domain knowledge, so on and so forth. On the other hand, I do think that there, as I also specified, we need to also think about how machine learning could be useful for those of us working in logic, because machine learning can address the fundamental question of how to arrive at knowledge from data. Okay, this is a short teaser, and as I mentioned, there is a longer paper which surveys results from the community on continuous and countably infinite data. Thanks very much.